Hi, everyone. It's great that so many people have signed up. We've had a record amount, over 1,500 sign-ups in total, and I've seen 335, 36 now attendees have joined the session. I'm just going to ask everyone if the sound is coming through loud and clear, so if people could let me know in the chat function that you can all kind of hear me. Perfect. Okay, fantastic, guys. Great. Well, hello and welcome to New Energy Updates webinar on achieving operational excellence in solar O&M. I'm Luke Brett. I head up solar projects at New Energy Update. I'll be moderating this webinar, and as you already may know, I'm putting together the PV Operations USA conference November 6th to 7th in San Diego. Now, this webinar is one of several of our pieces on what we're doing on optimizing the operational phase of the solar life cycle. As I said, there's over 1,500 people signed up to this webinar to get the recordings and whatnot afterwards. I see 355 people logged in. That number's going up. Excellent. So keep sending those questions in. Just a brief bit of housekeeping before we begin. This webinar will last about 50 to 60 minutes and is being recorded. And we will send you the recordings and presentations within a week or so after this session. Now, the purpose of today's session is really to take a closer look at the barriers when operating and maintaining a solar park and discuss which technologies are being used to cut operational costs. Joining me today to address some of these issues are Andy Walker, the Senior Research Fellow at NREL, John Previtali, who's the Director of Solar Technology at Wells Fargo, and Joshua Rogers, who is the Director of Solar Operations at Duke Energy Renewables. Now, all of the organizations involved today will be participating and speaking in San Diego for the PV Operations USA event. So if you'd like to meet them in person, then please do join us by registering through the website. Just search PV Operations USA and follow the links. Also, if at any points you want to ask the panelists a question, simply enter this into the text box, and we'll try to get through as many questions as possible during the Q&A session. Now, without further ado, I'd like to get Andy to begin with his presentation, kind of summarizing what the key challenges are in solar O&M and giving a market overview. So please do take it away, Andy.
Thanks for that introduction, Luke. Thanks to Luke and his colleagues at New Energy Update for giving us a chance to get together and talk about achieving operational excellence. And thanks to all of you at your computers for joining us today. And I look forward to the discussion, which you can participate in through the chat feature on the GoToWebinar. NREL's involvement in this is supported by Department of Energy Solar Energy Technologies Office, and Amar Kusaibati is our program manager. He's not only a manager, but he's really hands-on in terms of the research as well. And our team includes Tushar Agunda, data scientist at Sandia National Labs, Roger Hill, who chairs the IEC committees on some of these topics, and Gerald Robinson at Lawrence Berkeley National Lab. This group has, along with a PV O&M working group of over 100 people, put out this best practices document. It's now in its 3rd edition. Includes like things to think about in the design and construction of a plant, which we call prerequisites, standardizes definitions, talks about how O&M depends on this type of system, site, and environmental conditions, talks about system performance and O&M plans. And one of the improvements in this 3rd edition is to take paragraphs of text and kind of turn it into checklists. And one of those checklists reads like the table of contents that you should have in your O&M plan. Includes example work statements, a chapter on health and safety, provider qualifications, responsibilities, insurance, system monitoring, software solutions, and data management, which is something that we'll talk about today. We think sophisticated software is a way of achieving operational excellence. Talk about estimating PV O&M costs. And in a lot of reports, the appendices are kind of an afterthought, but in this case, they're kind of the meat of the matter, including detailed service descriptions, scopes of work, salary estimates, which we get from the National Bureau of Labor Statistics, employment qualifications, and the final appendices there is regarding the emerging IEC standards. So on this topic of digital O&M strategies, this is where we can really move the needle on operational excellence. Monitoring platforms, some of the best practices there are to record high resolution time series data, so we can really scrutinize down on the availability of the plant. And time intervals of less than 1 hour are common these days. 15 minutes is common because it often coincides with the utility billing average demand averaging period. The best monitoring systems include a comparison to a reference yield. Like, it's one thing to report what your system did, it's another thing to add what it should have done, so we like that. And those can be based on on-site pyranometers or satellite data for the coincident solar and temperature data to calculate what your plant should have done. And then a best practice is to report key performance indicators by inverter, or if you have DC level electronics, it could be by string or by module. When you lump things together into a plant, it's hard to tell which inverter is down if they're all the same size. And when you lump plants together into a portfolio, that tends to mask the underperformance of individual systems. And then not very many monitoring systems really reach into the DC side of the plant. So what's the approach for really inferring what the performance is on the DC side of the plant versus the AC coming out? And that's some of the masking that we'll talk about later. The best monitoring platforms track trends and provide diagnostics. So when a person generates a trouble ticket, they not only state that something is wrong, but provide some clues as to what might be wrong. So when the tech goes out to the field, he can fix it the first time. And here's where machine learning and artificial intelligence first come in. And so these are really hot topics, which provide an opportunity for us to achieve operational excellence. So machine learning and artificial intelligence are also being deployed in computer maintenance management systems. And these as a trouble ticket is generated by a monitoring platform, the CMMS ensure a timely follow-up. They can be used to track serial failures. If there's a batch of bad components, the CMMS data science can mine that data and spot that trend. And then it can also track the efficiency or efficacy of measures. So, what worked last time versus what didn't work last time in terms of condition-based or corrective maintenance. It used to be that PV systems operated themselves, or we used to say so, but nowadays with increasing penetration of photovoltaics on the grid and more sophisticated grid operations, operations is not a passive verb anymore. It's going to require active operations, often automated. A shutdown might be ordered by the off-taker or by the utility. The utility might require curtailment of a PV system output to accommodate the needs of the utility circuit. And then the utility or others might want to reach out to the inverter through controls and change the power factor, use the inverter to source reactive power, change the limits on voltage to respond to the immediate needs of the utility. So operations are becoming very active, not only for utility scale systems, but eventually we see the day when for all systems. And then down at the bottom here is a list of monitoring and asset management softwares that I was able to find on the internet. We don't recommend individual companies, but if I were to, you'll find them on these lists of monitoring platform providers. So as we talk about monitoring platforms and computer maintenance management systems, the topic of cybersecurity comes up. It could be a malicious insider, could be a malicious outsider, hacktivist unlikely to hack a solar system, but who knows? Could happen by accident. State-sponsored is on the list of cyber threats. So I have microinverters on my home, which are on my home network. If somebody were to hack in there and turn off my PV system, that frankly wouldn't bother me very much. It wouldn't harm me very much. But if they were able to do the same thing with 999 of my neighbors at the same time, then that would be a big enough disruption to probably bring our utility circuit down and cause a blackout. So it's that kind of aggregated control of DER assets, which distributed energy assets that pose the threat. And then it could be a gateway to other information, maybe on the same network that I have my microinverters plugged into. I also have my security system with control over the alarms and cameras, and I might have my building control system with control over my thermostats. I might have access to business information. So access to a network, something, it might be a denial of service. Somebody's preventing me from reaching out to my fleet of PV systems by continuously pinging them. And then there's the threat of ransomware coming in over email or any other browsing. I had a ransomware hit my computer, and rather than to pay a $75 ransom, I bought a new $1,800 computer. A lot of it relates to the network architecture, the topology and interfaces. Control of access is a place where we can achieve operational excellence, and the trend here is to classify types of data, like distinguish inverter trouble tickets from inverter set point control, who owns access to that, who has permission, and the trend here to achieve operational excellence is to push that need to know down into an organization. So really only the people that need to know that information have access to say, change settings or delete information. And then data privacy, maybe going even beyond the directives and requirements for data privacy. We can say that we're not liable because we complied with the directives, but it's better to actually protect our customers' data. Vulnerability assessments for DER devices and servers. NREL has a recent report out on how to assess the vulnerability of devices and components like inverters and other PV system components. Data in flight between a sender and a receiver. So this topic involves encryption and authentication. And then what's the patching policy? Like how often, sometimes hours matter and whether a patch is effective. So what are the updates rates? What are the sources of those patches? and guidelines within maintenance contracts for implementing patches. Now, I'm not a cybersecurity expert, so I rely completely on these standards off on the right-hand side of the screen. And initially, all we had was the NIST 800 standards, which were really designed for industrial control systems, but at that time they were the closest thing as applicable to PV systems. And now you'll see that some of the standards-making organizations like IEEE are coming up with standards for cybersecurity that are specifically related to PV systems, but these are still in their infancy. I also mentioned SunSpec Alliance as a kind of a standards-making organization which is active in this space. I wanted to talk about the different definitions of performance ratio. So the two key performance indicators that we pay attention to are performance ratio and availability. And when somebody tells you or reports to you what the performance ratio of a plant is, you have to look at the definition of it. So attempts have been made to standardize these definitions. The first two here are IEC standards, and all of them relate to energy out divided by actual energy delivery divided by estimated energy delivery. So the first one has the reference yield or the estimated energy delivery based on the standard test conditions. The second one on PV USA test conditions, and the third one takes that and corrects it for a balance of system efficiency, an age-related degradation, and a power reduction caused by an elevated temperature. And then the fourth way is to run a model like the NREL System Advisor model to generate the system yield, and then that'll be your expected energy, which you divide into the actual energy to get the performance ratio. So, of course, these different calculations result in different numbers. This table on the right is calculating the first three definitions of performance ratio for a population of 2,200 systems in the OSPARC database. Almost all of these systems are in California. And so the weather-adjusted one is the third one, shows an average performance ratio of 91.7%. And really, since that is adjusted for balance of system efficiency, age, and temperature, it should center around 100%. So it looks like there's about an 8% improvement in performance that ought to be achievable through optimized O&M. It's also a big spread in the data, and it's bigger for the third definition of performance ratio with a standard deviation of 16%, because that balance of system efficiency in the denominator of that PR adjusted is entered by the user of this database, and there's a wide variation in what they thought their balance of system efficiency was. So that's really kind of an unknown, especially when you consider that balance of system efficiency might involve soiling on the collector, which is really a performance ratio issue. So we're exploring with another definition, kind of a fifth definition, which is actually the product of performance ratio and balance of system efficiency. And then the second key performance indicator is availability, and here again, it depends on the definition. So there's raw availability, which would be just, okay, how many hours is my plant up and available and operating? Versus contract availability. And contract availability would apply varying exclusions, like, of course, all of them, any force majeure event that's beyond the operator control is excluded from the calculation of availability. If the utility is down, the grid is down, that probably gets subtracted from the calculation for availability. Some of them include if it's covered with snow. I've seen them include parts availability, like if we have to wait 2 weeks for a part, that doesn't count against our availability metric, and other varying exclusions. So here again, we've made an effort to standardize these through this IEC 63019, which tries to bin everything into availability categories. The availability definition was really developed for like gas turbines, where if any component of that is down, the whole plant is down, so it's either available or it's not. PV systems are actually characterized by this partial capability. If I have 5 inverters, maybe one of them's down, maybe 2 of them are down, but the plant is still available. So we have to distinguish between full capability and partial capability when we describe the availability of PV plants. And it'll be in service or out of service, and if it's out of service, it might be due to environmental conditions or requested shutdown, scheduled maintenance. And so this availability standard requires us to keep track of all the time periods and bin them into these different information categories. This also relates to the NERC GADS, which is Generating Availability Data System. They also require availability reporting on plants greater than 20 megawatts. And these kind of map to the 63019 data categories, but contact means it's up and running, resource unavailable, reserve shutdown, maintenance outage, planned outage, forced outage, and then the force majeure type stuff is out of management control. The letters here, like CIH stands for contact inverter hours. So NERC is trying to simplify it by just having the inverter report everything. So if the DC disconnect is open, then the inverter will be down. If the transformer is out, then the inverter will be down. So this, by capturing inverter hours, you should be aware that they capture both things upstream of the inverter on the DC side and downstream of the inverter on the AC side in their calculation of inverter hours. Here's an example of reports that we're providing for federal systems. There's about 2,900 systems on federal facilities. We think we need to get to 75 of them to get a decent sample size to characterize how that fleet is performing. And this one-page report is what we send back to the building owner. On the left-hand side is the PV system description with all the inputs that we need to put into the SAM model, System Advisor Model, a photo of the system, and then on the upper right, we report what the energy delivery was, what the expected energy delivery was, what the performance ratio calculated thus is, and what the availability is by sorting through the time series data. This chart on the right-hand side, the blue lines are what SAM says it should have done, and the orange lines are actually what it did. So we can look at, if you look at the third year in that graph, you can see there's 3 steps down. So there's 5 inverters on this system, 1 down, 2 down, 3 down, or the 3 steps down. And then you can also see how this organization's budget cycle works, because once a year they put in their budget request to fix stuff and go back in and fix it and comes back up. And then we also provide a comparison of how that system performance fits within a fleet of systems and a recommendation for resources that the building owner might go to improve performance. So I wanted to talk about, we defined the performance ratio, and I wanted to talk about how it gets masked by several factors. So the PR that my monitoring system reports might be a masked performance ratio, and that might be greater than the actual performance ratio. So some sources of masking include a low DC to AC ratio, so the inverter's undersized relative to the megawatt capacity of the DC side of the plant. That causes clipping, and that tends to mask some performance. And this graph at the right shows a system in Puerto Rico where you can see the effect of the masking. It's 125 kilowatt DC on a 100 kilowatt inverter. So if it's in clipping mode, I measure a performance ratio of about 80. I'm sorry, if it's not in a clipping mode, I measure a performance ratio of about 87%. And then when it is in the clipping mode, the DC side's providing 100 kilowatts and the inverter's providing 100 kilowatts. So the performance ratio looks like 1. It's actually 99.5. But so the masked performance ratio that might be reported at any time is greater than the actual health of the DC side of the plant. Instrumentation design can also mask performance and the maintenance of it. If I have a misaligned pyranometer that's not facing off in the plane of the array, or a dirty pyranometer, that'll report a performance ratio greater than the actual one. There's kind of a trend or a bad habit of reconstructing missing data by cutting and pasting from other time periods. That can mask performance problems. Oftentimes, if the meter's down, the plant is down in a sense in terms of generating revenue. The contractual reporting specifications can mask things like the exclusions from availability. And then again, reporting on a portfolio or a complete system rather than the individual inverters can mask performance problems. So we quantify this, and it depends on the climate, it depends on the actual performance ratio, and it depends on the AC to DC ratio. And for most common conditions, it's pretty negligible. Like if I had a typical PR of 90%, capacity factor of average, say 17.5%, AC-DC ratio of 0.66, which is pretty typical, if a little bit on the low side, then the masking that's caused by the inverter clipping is about 1.8, 1.9%. So pretty negligible unless your money is made on a narrow margin, in which case that 2% might be significant. But then we can see on the left-hand side of this chart that the masking to actual ratio can get quite high under other circumstances, like if the actual performance ratio is really low. So a dirty pyranometer is really easy to calculate. 10% soiling on the pyranometer basically means 10% higher performance ratio than you're actually achieving, but it's non-linear. So if the soiling gets worse than that, the masking caused by a dirty pyranometer is exacerbated. But notice that, you can get with a dirty pyranometer, you might be able to get 5 or 10% masking on the performance ratio, which again, if you're making your money on a small margin, might be significant. PV O&M depends on the application: residential, commercial, industrial, and utility scale. And specifically, utility scale is what's going to trigger the NERC and FERC type requirements and utility requirements and other things which add to our operations and reporting requirements. System type: is it on the roof? If it's on the roof, is it attached or is ballasted? If it's on the ground, is it fixed or tracking? Is it a carport system, which will require 2 people to go to the site and some kind of man lift? Components, make and model. And, this is actually probably the most important thing of this whole presentation. Remember when we were talking about the computer maintenance management system, the CMMS? More than anything else, your O&M cost is going to depend on the make and model of components. There just are certain manufacturers, or maybe even within certain manufacturers, certain serial numbers or certain model numbers, which are more problematic than others. So if you can keep track of that and use it to inform your purchasing decisions, then you can achieve operational excellence. Micro string versus central inverters, they affect both the cost and the reliability of the system. Micro inverters, if talk about this partial availability, some of them are going to be up at any given time, but also some of them are going to be down at any given time. So whack-a-mole is a term that comes up in micro inverter maintenance, but in general, micro and string inverters might have some reliability and other advantages over central inverters. Central inverters have the advantage of a low cost. Fixed versus tracking. How about the site? Is it a remote location, or is it near an urban area where we already have active operations? Access to the site: is it a dirt road that might get muddy? Environmental conditions, sources of dirt. It's our theory that dirt doesn't just happen. It comes from agricultural plowing or diesel soot or bird populations or some specific source of dirt that might be associated with the environment: high temperatures, high wind, snow, and extreme weather. So we have been working on this cost model. An online version has been developed and published by SunSpec Alliance, and the URL for it is listed here. But we still get a lot of demand for an Excel spreadsheet version. So if you'd like to have a look at that, please email me. And there's also a document here that describes the methods behind it in this blue box at the bottom of the slide. So feel free to contact me if you'd like this spreadsheet version. O&M costs are, typically reported between $10 and $20 per year, but numbers as low as $0 per year and as high as $40 per kilowatt per year are also reported. But the whole dollars per kilowatt per year metric is problematic because it varies from year to year, and it varies with all those dependencies that we talked about on the previous slide. So what this cost model does is, for your specific situation, it tries to add up all the administrative, preventative, corrective, and disposal costs. Other administrative things like insurance tries to add up all those costs. The preventative measures are on a schedule, 1 year or 5 years. The corrective maintenance is according to some Weibull failure distributions that we get from our colleagues from the PV ROM database at Sandia. And so the outputs are shown on the right here. So the blue bars are the sum of those costs that occur in each year. And so for this 10 megawatt ground mounted plant, they start out less than $100,000 a year, but they climb to over $300,000 per year. What those Weibull distributions tend to do is to squash out a failure over a course of time. Like it might say the failure rate of an inverter in this year is 1%, and then the next year 2%, and then the following year 1% again. It's like a bell-shaped curve. And so inverters don't actually fail that way. They fail all at once. So we also do this reserve account calculation that says, based on a binomial combination of what might fail and what might not fail, how much money should you keep in reserve? In the early years, it's not much because warranties cover everything. But in the later years, it gets up to about $800,000 a year that you should have access to in the form of a line of credit or a reserve account or some source of revenue to fix the system so it's not down while you try to find money. And the parts that you actually have in inventory, like if you've got a stack of modules in a shipping container or something like that, that actually counts against this reserve account. So you'll notice that these costs go up over time. They go up in year 10 because the warranties expire, inflation raises the parts and labor prices, and these failure distributions that we get from Sandia show high failure rates in the later years. So the O&M costs in the later years are significantly higher than early in the life of the plant. And then the orange line puts us on a cents per kilowatt hour basis. And that gets even worse because we're factoring in a 0.6% per year degradation in the kilowatt hour output of the plant. So in the final years, the O&M cost is up around 2 or 3 cents per kilowatt hour delivered. So just to continue with this example of this 10 megawatt ground mounted plant, here's some of the results. If I took those costs and annualized them over the course of a year, it'd be $126K or $12 per kilowatt. The reserve account maximum was $800. And the very bottom line, over the whole life of the plant, we were annualizing about 1.1 cents per kilowatt hour. Once we have it in this Excel spreadsheet, we can use the pivot table function to dice it and slice it and make Julian fries. We can report by category, by component, by service provider, other user defined ways that you might want to sort out the individual O&M measures that are added up for that. So, and then the one outlier, or the one, I don't know what potential surprise might be, severe weather events. These are in the European version of this best practices document. They're called extraordinary events. And they might include hurricanes, tornadoes, earthquakes, hail, flooding. It might include wildfires in that, although about half of the claims related to PV system fires are caused by the PV system itself. And so remember, Tushara Gunda at Sandia is collecting a lot of this information, these trouble tickets from the CMMS systems, and she did a word search on them, or applied her data science version of that. And hurricane pops up with over 700 records related to hurricane damage. Snow is the second biggest. Temperature, storm events, weather conditions, hail, high wind, lightning, flooding, all contributed to these trouble tickets related to PV systems. And this data reflects where the systems are located. So the map at the bottom shows where, and you might be surprised that hurricane is the biggest bar on the bar chart. You might say, well, we don't get very many hurricanes. And it's because most of these systems that are reported in the bar chart are coming from from North Carolina there. And also there's a lot of systems in California. But the fact that most of these systems that are reporting into this PV-ROM database are located along the eastern seaboard there, that's why hurricanes are showing up as the biggest part of this bar chart. I want to make that clear. And so these severe weather events are site-specific. Hurricanes are along the eastern seaboard. Tornadoes in Tornado Alley, Texas, Oklahoma, Kansas, Nebraska, Colorado, South Dakota, also in the southeastern United States. Earthquakes in Alaska and California. Hail is a phenomenon in Colorado and Wyoming. Flooding, Florida, Louisiana. So these threats are site-specific. So a little bit on hail damage. The photo on the right there shows a hailstone bigger than a golf ball, but that photo on the right is actually a success story. There's about 200 or 300 kilowatts of PV in the background of the photo, and not a single one of those PV modules was broken in that particular hailstorm. But the other photos come from a later hailstorm where there was larger hailstones. And you can see some damage. I call this photo in the middle the starry night. You can see that the hail caused breakage on 3 of the modules, but one's unbroken. And what would happen is a hailstone would cause a crack, and then when future hailstones hit it, it would continue cracking more. It doesn't mean that the one on the top of the photo is okay. When we brought it back to the laboratory and looked at it under electroluminescence, you could see the cracking that was caused by the hailstone impacts, the cracking of the PV cells themselves. So they're actually replacing even the ones that don't show the glass cracking. And then for the unframed modules, the damage was worse. You can see the broken off corners of the unframed modules. So what do you do in a situation like this? First of all, after the storm, hailstorms happen suddenly and unexpectedly. So after the storm, shut the system down, conduct a physical inspection, and then electrical testing, specifically the integrity of the conductors and the integrity of the grounding system. And then make decisions about whether it should be removed. If it's a small system, you might not replace it. You might take that money and put it into a big plant somewhere, or repair it by replacing individual modules or replacing the whole thing. And then once those repairs are complete, take it through a recommissioning process. So in the system on the right here, that one was replaced by about a third of those modules are broken, and that entire system was replaced by hazard insurance. The one in the middle was just customer owned without that kind of hazard insurance, so that was a loss to the asset owner. So hazard insurance is the cure for this risk. High wind.
Sorry, Andy. I'm just in the interest of I really appreciate obviously the slides, but just in the interest of we have about 20 minutes left just for the kind of panel discussion on the webinar. So if it's all right, I'll just let everyone know obviously that we're going to be sending out these slides. Obviously, you have questions, do let Andy know, so we can all go through these presentations at a later date, and then also folks who are asking the questions. Yes, we'll be sending out the recordings and the presentations afterwards after this webinar is complete. I was just going to quickly ask a couple of questions to our panelists, John and Joshua. John's from Wells Fargo. He's the director of solar technology, and Joshua's from Duke Energy Renewable, and he's the director of solar operations. Excellent presentation, Andy. You did give a really great in-depth insight on what's going on in solar O&M and some key challenges. But I wanted to just quickly dive into a couple of questions with regards to data transmission and management, which is a key challenge in the solar industry. And I do hear at Wells Fargo is helping to kind of address that problem. So, John, could you just elaborate on this?
Yeah, sure, I'd be happy to. So we've been involved in what's called the Orange Button Initiative for a few years now. And by the way, Andy, great presentation. Thank you so much. And I really enjoy the collaboration that you and I have had for over a decade on this topic. But the Orange Button Initiative is a DOE-sponsored effort that has created a taxonomy or a dictionary of over 5,000 unique terms and definitions that are used by the solar power industry, and also incidentally used by wind power and other renewable energy sectors. And it's free. It is available through the SunSpec Alliance, or if you contact me or Tom Tansey at the SunSpec Alliance, will send you the taxonomy directly in the form of a spreadsheet. And it's really a great tool to expedite the transmission of data across different company firewalls and between business systems. So just briefly, one of the biggest problems that we have is that we receive data from our customers, things like monthly operating reports, a long list of due diligence documents, insurance certificates, everything like that, in a wide range of different formats. And not only is the data management requirement burdensome in handling these different formats. Actually, within each document, the terms and definitions are often subtly different. And so it's very difficult to make these machine readable, to automate the processing of this information. So the orange button taxonomy intends to fix that problem. Right now, at companies like yours, you probably have software developers and IT people developing, or maybe they already have developed lists of terms and definitions that you're using to develop your business systems and databases. And I wouldn't be surprised if those terms and definitions are unique to your company. We are hoping that our customers and the solar industry in general will stop doing that and start using the orange button taxonomy instead, so everyone can speak the same language. The last thing I'll mention is that a list of 5,000 different terms and definitions sounds very unwieldy. So one of the most important things that we've done is to actually categorize the terms and definitions into what are called abstracts. So an abstract is a particular sort of subset of terms and definitions that are useful for a particular purpose. So for instance, there's an abstract on monthly operating reports, all the terms and definitions typically used for that. There's an abstract on site lease agreements. There's an abstract on different financing mechanisms like sale leaseback and partnership flip. So with that, I'll stop there and hand it back to you, Luke. Thanks.
Oh, perfect. Well, I mean, that's really good insight on what you're doing at Wells Fargo to address the issue of data transmission and management. Joshua, what other kind of programs are you implementing at Duke Energy that's kind of shaking up or optimizing solar O&M in general?
I mean, a couple of things, particularly in the standardization side of things. So as John just mentioned, getting to a standardized way of not only documenting issues, but also the resolutions and how we manage that data on the back end. So essentially, a lot of it's machine learning. Essentially, Andy mentioned some of the stuff around data scientists. We're using a lot of information there to really pull in and look at conditional-based monitoring as far as our equipment goes, and really empowering the field for first-time resolution to faults and downtime. So, O&M, a lot of the costs are, hey, equipment's down, somebody's going out to assess it, and then what they need is parts and equipment and possibly additional resources to fix it or repair or a warranty claim for the OEM. So a lot of it's taking, that information, standardizing it, getting procedures, references, and work orders at the fingertips of the technician through digitalization with iPads and field technology. A lot of the different decisions also are going to be based on PPA rates, downtime, actual forecast. So not just responding to every single fault, kind of bundling that work and really making sure that we're optimizing our resources. As Andy mentioned, there's a number of sites, many of them in remote locations all over the place. Many operations teams are very limited in resources. So just managing your resources accordingly can really have an impact on those O&M costs, as you mentioned, that have a very wide range based on the variations from, everything from site equipment to location, and just site-specific that make benchmarking tough. So those are just some of the initial stuff. Other things that we're really focused on is drone scans and pulling out some of the roadblocks as far as utilizing technology to streamline some of our maintenance practices.
Perfect. I mean, obviously, a lot of that is kind of the theme of identifying underperformance. And I was going to ask John again, actually, refer to you. So what are you kind of talk a bit about some of the primary sources of underperformance that you actually see in your portfolio at Wells Fargo?
Sure. Yeah, well, there is sometimes a disconnect between the energy production estimate and the actual performance of the project. And the primary sources of underperformance are potentially too optimistic weather files in some cases. As people probably know, they're generally like 4 or 5 different weather files that you can use for the production estimate, and some of them can be up to 5 or 6% higher when you take into account direct normal insolation in addition to global horizontal insolation in the production estimate. So even though the irradiance doesn't look like it is 5% greater for a particular file, when you actually run it through PVSys or the production estimation tool, it turns out to be causes 6%, 5 or 6% higher energy production estimates. So we think that's the biggest source of bias. There's also potentially room for improvement in estimating downtime associated with things like inverters, right? Right now we estimate generally like about a 1% downtime for utility scale projects. It's probably a little bit higher than that. And then another big source is related to soiling and washing. We're finding that operators are having a hard time keeping up with the washing schedules that are essentially predicted or planned for in the energy production estimates. The other thing I'll mention is that the way that independent engineers estimate downsides, so people may know what P cases are. They stand for probability of exceedance values, and the average P value, which is called the P50, is what we use for the pro forma production estimate. But at the bank, we also have to account for what are called downsides. So these are cases where you don't have as an average performance, and downsides are known as like a P90, P95, P99, and typical sources of downside underperformance are interannual variability of weather, the measurement uncertainty, allowance for the weather sensors, and I apologize, there's one other source that I don't recall right now. But in all actuality, it's likely that we know that there are many other sources of uncertainty. And so what we're starting to do is to, encourage people to start thinking about considering things like uncertainty around module degradation, uncertainty around availability, soiling, as I mentioned before, and other things that contribute to the energy production estimate, but aren't typically included in that downside analysis.
Okay, so obviously, Andy, what you were kind of talking then, obviously, there's a considerable amount of planning that must go ahead, when enacting these kind of O&M strategies. I was going to ask Andy, obviously, your work at NREL, and you were dissecting a lot about the kind of recipes for an O&M plan and things to consider. I would like to just ask you that question. What does an O&M plan contain?
That best practices document, the link which was on my first slide, that has a checklist with all the things the O&M plan should contain. It's too detailed to go over right now, Luke, but in contact information, some of them obvious, like the O&M provider, some of them less obvious, like people at the local jurisdiction and emergency service providers, as-built drawings, warranties, how to read the operational indicators, inventories of spare parts, sources of spare parts, details about where those parts appear in the system, how the performance metrics are defined and reported, training that's required, requirements for chronological O&M logs, how to respond to alerts and alarms. That can, again, too much detail to go in right now, but that kind of thing, Luke.
Yeah, no, I understand. I mean, in terms of planning, also, obviously, a lot of these sites are aging, coming, out of warranty. And I was going to ask Joshua, what's Duke Energy's long-term strategy for dealing with aging sites?
Yeah, so a good portion of our current portfolio in our commercial assets for solar and wind are aging, and many of them are actually already out of warranty. So as far as tackling these aging sites, what we're really looking at is discovering, researching, and building business cases for repowers, and a lot of that's based on failure data. We don't have a lot of that, so I would say that that's not necessarily the first thing that we're doing, and it's not necessarily a priority, but it's definitely on our radar. The things that are our priorities right now, and what we're really building our strategies around, is conditional-based monitoring and really understanding our assets. And that, as we mentioned, the OEMs, or the original equipment manufacturers, that performance varies based on the equipment and how you take care of it. So we're using data analytics and machine learning to really understand where is our equipment failing, what is the failure rates, and what are the specific failure modes. And not just understanding the immediate failure mode, but what are some other underlying causes. Everybody looks at, hey, these inverters are failing. And the immediate answer is, oh, it's the OEM, the inverters fail, that's just the answer. However, we've seen several sites where you pull back the layers and we see failures caused by site trips or improper grounding or external AC breaker operations, and different things that can be controlled. So we're really digging into not just the immediate cause of failure, but the actual root causes and possible things we can change long term based on the data that we have from the sites that have been operating for quite some time. The other thing with that is, sorry.
Yeah, please go ahead.
I was just going to say the follow-up there is, once we have that information, really building a strong technician team with retention, expertise, with the appropriate training to utilize their skills and expertise. Once these sites come off a warranty, some of the maintenance handcuffs are now removed to where you can go in and fix this without waiting on an OEM for several weeks. So sometimes the repair times can improve. And really what that's going to be based on is, do you have the failure data? Do you have the training and the technicians and resources in place? And then lastly, what Andy just mentioned was, do you have the spare parts strategy as well to make sure that you have those critical spare parts to bring that equipment back up in a timely manner? So all that's taken into consideration, and then, like I said, worst case scenario, what is that business case for Repower after that?
Sure. And John, you had some insight.
I just wanted to agree that site commissioning, basically running the test before the EPC leaves to make sure there are no ground faults, will save a world of problems for you, prevent a world of problems for you going forward. With regard to inverters, as people know, those are the number one source of issues. So as Josh mentioned, making sure that your technicians are certified through the inverter company training program to do the warranty work is a great time saver and force multiplier. Another thing that we're starting to see is time to respond service level agreements with penalties for inverter technicians to come out and make sure that repairs are done in a timely manner. An example is like with Schneider Electric leaving the inverter market in the United States, we're seeing some real problems with delayed service. So you want to make sure that you don't run into situations like that. And then I just want to emphasize how important it is to have unique spares, as Josh mentioned. So most inverters, as you probably know, are built with off-the-shelf components, but there are some unique spare parts that are needed, specifically things like control boards. So I encourage people to stock up on those, have a warranty agreement or a service agreement with the inverter company that says that if the control boards are improved, they'll swap out the control boards that you have in your warranty, but it's great to have those unique spares available. The other thing I just wanted to mention, and incidentally, I did remember that third source of uncertainty. It's model uncertainty, for those who are wondering about that. But the other thing I wanted to mention is how important it is to try to not be fooled by masking underperformance. Andy mentioned this, that when pyronometers are dirty, it looks like the plant is doing better because the pyronometers, the fuel gauge of the systems, are not absorbing as much light. So it doesn't look like the plant is getting as much light, as much irradiance as it actually is. So it's easy to be fooled into thinking that the plant is performing well. And that's really problematic for us particularly because, obviously the plant is not generating as much revenue as it could be if it's not washed on schedule, if it's if trucks are not rolled to fix inverter problems because it looks like the plant is actually performing as expected when it's weather corrected using that masked or that reduced irradiance measurement from the pyronometer. So yeah, I encourage operators not to be fooled by masking and actually simply perform the work that has been scheduled in the O&M agreement and budgeted in the O&M agreement.
Perfect. Unfortunately, these webinars go so quick. We've only got 4 minutes left, but I'm just going to quickly ask. There's been quite a few questions coming through on inverters. So Josh, just your last kind of thoughts on there. Someone's asked, what is your strategy and expected costs for inverter replacement?
Yeah, good question. As far as inverter replacements, that's something that, like I said, we're still analyzing as far as our models. It has changed, over the last 6 months, a year and a half. We've fluctuated with some market research that we've found, essentially shifting, what our replacement percentages are for the plants based on initial modeling for sites and O&M costs overall. As far as strategy for existing sites and what we're actually doing, like I said, a lot of our investment right now is in training our technician teams, building that retention and expertise and parts. And we have seen some successes there with, getting that manufacturer certification and training, getting parts in place, and getting the confidence to repair those inverters. And what we've seen is, we actually have inverter manufacturers that have gone out of business. Those were our lowest performing inverters. And actually, a small success story, these sites are 7-8 years old, and now those inverters that are out of warranty, manufacturer's gone, we actually have them performing higher than some of the leading inverters in the industry. So, I think a good thing that I'll say is inverters are very much like a car. If you buy an expensive car but don't take care of it with the right maintenance, the right technicians, it's not going to run optimally, and it is going to have issues. Same way with an inverter. If you're doing maintenance but you're not doing it thoroughly, you're not doing it at the correct intervals, you're not taking care of it seasonally, all those things are going to have impacts long term. So I think, understanding the equipment, having the right teams and individuals on the ground that really understand, hey, if I'm not checking this torque, it will come back to bite me. If I'm not looking at this AC contactor in a very specific way and where it's failed previously, then it will come back to bite me with downtime. So I would say, to answer that question, inverters are going to be the ongoing challenge. And, having, part strategies that don't necessarily always go back to the original manufacturers. A lot of these manufacturers of inverters use parts that are manufactured by all sorts of people. So you could take those specs, and once they're out of warranty, get that equipment back up online, likely quicker and possibly even cheaper. So that's really where we're going with our strategy, at least currently. Hopefully that answered the question.
No, absolutely. Well, unfortunately, these webinars just went very quickly. There's a lot of questions that came in, so I'll be kind of sending them, distributing them around afterwards. And that's all we have time for today, but there's some excellent content. Big thanks for Andy for introducing this. Excellent presentation, some really positive comments on the data sets from the audience too. And Andy and Josh for taking part, giving your thoughts. It was definitely very stimulating. Of course, we'll be sending out the full replay and presentations 1 week from now. So do share them with your colleagues and the broader solar community. But what's most essential also is that we have plenty more to cover. John, Andy, and Josh will be joining us at PV Operations USA this November, 6th to 7th in San Diego. So we do hope you can join us there to continue the discussion. And of course, if you have any questions, send them my way, luke@newenergyupdate.com. Thank you for tuning in. I really hope you enjoyed the webinar. And of course, if you have any questions, send them my way afterwards. Thanks. Bye-bye.